We're making major investments right now in our 5G network, and it's important for us to understand what are the types of applications and what are the uses of that network. Because of the breadth of research domains and expertise, the University of British Columbia gives you the ideal setting for a wireless living lab.
My research work has concentrated on wave propagation systems. Strong earthquakes do happen, at least one per year in BC. Where it will happen, we don't know. When you have a large disaster like an earthquake, critical infrastructures like the power grid, the water system, transportation system, they all get affected simultaneously. The idea of having these early warning systems is we can see where the earthquake wave is going and how strong it is. In terms of minimizing the damage, there are two things you can do. You can reinforce the system before the disaster happens, and then you can bring the system back up as quickly as possible. There is a number of components in an earthquake wave. The P wave is tiny in magnitude, but it travels faster than the S wave, the strong wave. No two earthquakes are identical to each other. To guess what the S is going to be that accompanies a particular P is very, very difficult. In this project, instead of measuring the very small P wave, we are measuring the much stronger S wave. We can do that with sensors that are much cheaper. Of course, the amount of network traffic that we will have is huge. So that's where the MEC computers come in. We bring that information to the MEC, and then we have to synchronize the waves. Once it's been delivered to the MEC computer, we can predict the amount of damage that will happen all across the city. This information can be used by the infrastructure owners to take actions at the level of the power grid or transportation system automatically. That information is very important to the disaster responders. Time is of essence. We're talking about a very extensive network of sensors. One of the strategies to deal with very large systems is to partition the system into sub-areas. We can allocate different MEC computers to different parts of the city, which means that it will be much faster. In the case of early warning, an earthquake, we have maybe 20 seconds ahead of time. The latency time is not the same always. It depends on the traffic in the network at that moment. So in 5G, the error between one sensor and the other may be 1 or 2 milliseconds, as opposed to 10 milliseconds. The lower the latency that the technology can offer us, the more accurately we can capture the waveforms.
This is our sensor board. This is a Raspberry Pi computer. And on this is the ADXL355 accelerometer to measure the seismic waves.
We have tested LTE-Cat M1, LTE, and 5G sub-6, and subsequently we will be able to test the millimeter wave technology with the 3 stations around UBC campus.
We can do a lot on paper, but unless we take it to the field, it doesn't have any value. The field would be the city of Vancouver. In order to make use of this approach, you need a telecommunications technology with low latency and high processing capability. Our experience with Rogers 5G is excellent. The people in Rogers are very knowledgeable and have helped us a lot with the interaction between what's physically possible with the technology and what algorithmically we can do. This would not be possible without 5G and the MEC computers. We cannot prevent disasters, but my hope is that with the tools we're developing here, we will be better at managing them, and therefore we will save lives and property, mostly lives.